Hey, this video is about how to solve logarithmic equations. And so when we solve exponential or logarithmic equations, what is really, we use a whole lot of is the inverse properties. And so we learned this on a different video, but it was about logarithmic properties. If you take a and you raise it to the exponent log base a of x, the fact that logarithms and exponents are inverses of each other, they undo each other, is why if you raise a to the log base a of x, you just get out x. And also if you take a logarithm of an exponent, log base a of a to the x is just x. These are inverses being applied in both of these cases. We're going to take advantage of this information and solve these logarithmic equations. So if you've never seen this before, it's a little wacky, but it works really well. So let's just take number one. Number one is this: log base 2 of x is equal to -3. Okay, this is what I have. I'm trying to solve for x. Well, I'm going to look at this and say, if I were to raise both sides of this equation by the base. So what is the base? This is the base 2, okay? And so I want you to look at this. If I were to raise both sides by the base 2, so what I mean is raise both sides of the equation to the power. The base 2 raised to this is equal to the base 2 raised to this. 2 raised to this power equals 2 raised to this power. And this is what is wacky. People maybe have never seen this before. 2 to the this equals 2 to the that. Then I have this situation right there. And a raised to the log base a of x, these are undoing each other. 2 raised to the log base 2 of x, these are undoing each other. And I simply get 2x is equal to 2 to the -3, or 1 over 2 cubed, or 1 over 8. That's what that equals to. So x is 1 over 8 for that one. How about here? Look at number 2. This is the log. What is the base here? We don't see it, so we understand it to be the common log. So this is the base 10. This is a 10. How can I solve this? The same way I just did this one. I'm going to raise both sides by the base. 10 to the this equals 10 to the that. 10 raised to the log base 10 of x. These are undoing each other. I just get x is equal to 10 to the 1st power, or 10. Just like that. How about this guy? This is ln of x is -2. What is the base here? Ln. Well, the base is understood to be the natural base, e. So this is, if you want to think of this as log base e, you can. It's the same thing. And so what am I going to do? The same thing I did a minute ago. Here and here, I'm going to raise both sides by the base e. E to the this equals e to the that. E raised to the log base e of x is the same thing as a raised to the log base a of x. These are undoing each other. X is just e to the -2. All right, that is this. This, for instance, let me take this for instance. This is called the exact answer, the exact form of the answer. If they wanted an approximate form, then what they mean when they say find the approximate form, that means put it in your calculator and round to whatever they tell you to round to. So if they say round this to the nearest tenth, maybe, you would put that in your calculator. And so you would say e raised to the -2. And you get 0.1353. X is about 0.1353. If they wanted it to the nearest, let's say hundredths, that would be x is 0.14. This is approximate answer, and this one is the exact answer. So depending on the instructions that you're given will determine how you answer these, okay? Most of the time I just ask for exact, but if they say round to a certain number of places, they want you to stick it in your calculator. All right, let's look at number 4. I'm going to erase those so I have a little more room. Number 4 says solve this. Log base 5 of 8 minus 7x equals 3. Okay. Well, we have a logarithm by itself on one side of the equation, which means we can apply the same principle we've been doing. So what I'm going to do is raise both sides of this equation by the base, and the base is 5. I'm going to say 5 to the this equals 5 to the that. 5 to the log base 5 of whatever is just the whatever. So what's coming out over here on this side is 8 minus 7x. What's coming out on this side is 5 to the third power. All right, so we get 8 minus 7x is equal to 125. Let's solve for x. Now this is just a linear equation. Subtract 8 from both sides. Oh my goodness, what is 125 minus 8? I have to borrow 15, 1, that's a 7. It's 117, I believe. Divide by negative 7, oops, and you get negative 117 over 7. That's the exact answer for number 4. All right, 5. Finally, we have something a little bit different. In each one of these cases, we had an isolated log expression. This time we do not. We have 2 log expressions. So what we have to do is combine this into one. So we've already learned, using the log properties, how to combine things. When there's a plus, we can combine this through multiplication. This is the product rule. So we will apply the product rule for number 5. We're going to apply the product rule. First, let's write this as one log expression. So this is equal to the log of x times x minus 9 equals to 1. We have done nothing on the right-hand side of the equation. Now we're ready to do what we've been doing, applying inverse property. What is the base that we see here? Since we don't see a number, we understand it to be 10, the common log. So we'll say 10 to the this equals 10 to the that. What's going to happen here is 10 raised to the log base 10 of x. These are undoing each other. So we're left with x times x minus 9 is equal to 10 to the first power. Let's solve this equation. This is going to turn out to be a quadratic equation, x squared. So we'll have to use quadratic methods to solve this. X squared minus 9x is 10. I'm going to get a 0 on one side. X squared minus 9x minus 10 equals to 0. And I think this will factor. X minus 10, x plus 1. Let's see, x squared minus 9x minus 10. Okay, so then we get that x is 10 or x is negative 1. Now, this is a logarithmic equation, and logarithms have a domain issue, right? If you think of what a log graph looks like, it looks like this. So the domain is 0 to infinity. So the domain is, you can only put positive numbers in there. So you got to check your answers at the end to make sure you're not getting into trouble. So go to the original problem here and put negative 1 in here. The log base 10 of negative 1. Oh no, I'm not allowed to put a negative there. You totally reject that answer. That's no good. Try the other one. 10. Log base 10 of 10. That's positive. That's okay. 10 minus 9 is 1. That's positive. That's okay. We got one good answer out of that one. So that's how you would do number 5. All right, let's make some room and do 6 and 7 and 8. And these are pretty straightforward. Number 6 goes like this. It's kind of the same situation as we had in number 5. We have 2 different log expressions, and we need to be able to rewrite this as one expression, and so we're going to use a log property. Since there's a plus sign, we're going to use the product rule. So this turns into, number 6, it turns into log base 2 of x plus 1 times x minus 1 is equal to 3. Now I've done nothing on the right-hand side. I just rewrote this using the product rule. Now it's ready. Let's raise both sides by the base. 2 to the this, 2 to the that. 2 raised to the log base 2 of this is just this. X plus 1 times x minus 1. When you multiply these together, since these are conjugates, you get x squared minus 1. 2 to the third power is 8. Let's solve this using a quadratic method. How about let's just take the square root of both sides. Let's add 1. X squared is 9. Take the square root of both sides. So x is equal to plus or minus the square root of 9, which means plus or minus 3. X is 3 or x is negative 3. Now, since this was a logarithmic equation, I have to make sure this is in my domain. Put in 3. 3 plus 1, positive. 3 minus 1, oh wait, where's my original? Here it is. 3 plus 1, positive. 3 minus 1, positive. You are okay. Negative 3 plus 1, negative. Oh, the moment you find it's no good anywhere, you just reject it right off the bat. So we got one good answer for number 6. Okay, let's try 7. 7 I'll rewrite over here. It is log of x plus 8 minus log of x plus 1 is the log of 6. Okay. So in order to solve log equations, we need to isolate the log expression. Okay, so that's what we've done in all of these cases. It either came to us isolated by itself on one side of the equation, or we worked on it to get it by itself on one side of the equation. There's a couple of issues here. We could totally rewrite this as one logarithmic expression using a log property called the quotient rule. So let's do that. Since there's a minus, I'm going to rewrite this into a fraction. This turns into the log of x plus 8 over x plus 1. And then this is equal to the log of 6. Now, we've got two choices. One choice is to subtract the log of 6 to this side and then use another quotient rule and rewrite it again to get one log expression on one side of the equation and a 0 on the other. We could do that mathematically, it's correct, and there's nothing wrong with doing that. However, there's an easier route, and I like to go the easier route when I can. So right here, when we have one log expression is equal to another log expression, this is isolated. It counts as being isolated. They're separated by this plus, by this equal sign. So I don't have to do that extra work. I can say, oh wait, this counts as being isolated. I'm ready to apply an inverse. Let's raise both sides by the base. The base is 10 because we don't see it. So it's going to be, I'm going to write this in for emphasis. 10 to the this equals 10 to the that. 10 to the log base 10 of something is just the something, x plus 8 over x plus 1. 10 to the log base 10 of something is just the something, is 6. Now, I can solve this by cross multiplying or by multiplying both sides by the denominator. Either way, you get the same thing. 6 times x plus 1 is equal to x plus 8 times 1. Which is just x plus 8. This is a linear equation. 6x plus 6 is x plus 8. I'm going to subtract x from both sides, and I'll get 5x. I'm going to subtract 6 from both sides, and I'll get 2. I'll divide by 5, and I'll get x is 2/5. Now, let me just double check that works. 2/5 plus 8 is positive. 2/5 plus 1 is positive. This is a good answer. Okay, the very last one, it's going to be similar. We have the natural log of x. Minus the natural log of x minus 4 is the natural log of 3. I rewrite this into one log expression. Since there's a minus, we're going to use quotient rule. This is the natural log of x over x minus 4 is equal to the natural log of 3. All right, again, you could subtract this and rewrite it into one log expression equals to 0, but you don't have to do that. This counts as being isolated. One log expression equals one log expression, isolated. Apply your inverse. This is natural log, which means log base e. What I'm going to do is raise both sides by the e. I'm going to say e to the this equals e to the that. E raised to the log base e of something undoes each other. It's just the something, x over x minus 4. E raised to the log base e of something is just the something is equal to 3. I'm going to cross multiply and solve. X times 1 is equal to 3 times x minus 4. I get x is equal to 3x minus 12. I'm going to subtract 3x and get minus 2x is minus 12. I'm going to divide by negative 2 and I'm going to get x is 6. Let me make sure this is in the domain. Go to the original. Natural log of 6, positive. 6 minus 4, positive. You're good. All right, so that is how to solve logarithmic equations.